Hello, my name is Lucia. I'm a master's student in the Department of Mathematics and Statistics at BU, and today I'll be presenting a reflection on my IGS Graduate Summer Fellowship from earlier this year. So here's a roadmap of my presentation. I'll start with a project overview, a test case implementing a paper on sea surface temperature prediction, an extension to the weather variables that we are interested in, and some acknowledgements. So first, the big picture goals. The overall goal of the project is to develop a model that can reliably forecast weather, and specifically rainfall, in the Ghana region. There are some challenges associated with this prediction problem. The first is that rainfall is notoriously difficult to predict, especially in tropical climates like Ghana's, and especially from real data, which is what we're interested in. One reason for this is that rainfall is affected by dynamic systems that involve many other weather variables, such as wind, pressure, temperature, humidity, and many more. There are two main frameworks for forecasting in a dynamic system. The first is purely data-driven, but these approaches don't always perform well for this kind of problem. The second is physical approaches, or what's called numerical weather prediction, which involves modeling systems of all the weather variables directly. However, this is computationally expensive and difficult to do. One idea is to blend the two methods using deep learning to use both data and physics and have a combination of the strengths of both. Now I'll move on to the test case of sea surface temperature. So this is from a paper de Bezenac et al. 2018. This is their model architecture, or their approach to predicting sea surface temperature. The idea is to take 3 to 4 input images. These are single daily observations of sea surface temperature in a given region, input it to a convolution-deconvolution neural network that I'll show you in the next slide, and infer from those 3 to 4 previous images the motion field or the wind vector field, then to combine that predicted wind vector and the previous images in a warping scheme. You can think of this as like a weighted sum or a matrix multiplication, to then output the predicted next day of sea surface temperature observations. So that's one iteration of the model, and over many training iterations, there is supervision that is comparing the observed image with the prediction and trying to minimize the distance between those two images. So here is their model in detail. You'll see again, these are their 64 by 64 previous images. This is the outputted wind vector field, and in between you have a series of convolution and deconvolution steps with skip connections. This is a very common convolutional architecture for neural networks. So after implementing this model and getting it working on sea surface temperature, I wanted to extend this to land temperature and other variables that we're actually interested in predicting. To do this, we started with ERA 5 simulated weather data, for which we have access to many more variables in the Ghana region, including both temperature and wind. So now the idea is, can additional supervision or additional constraints on the predicted wind improve the prediction results? So here is the updated approach that we're taking. It's very similar to the previous one, but now we have an extra supervision step on the wind vector. And here's an example of an output that is pretty good, but is also exhibiting a problem that we're seeing elsewhere, which is that the model is actually learning sort of like an identity map from the previous input image instead of predicting the actual ground truth next image. We're not really sure why this is happening, but we're actively working to address it. Some examples of what we're trying are inputting more variables than just temperature and wind. We're trying to simplify the loss function and simplify the architecture itself. And hopefully eventually we'll have something that does reach the goal of improving weather prediction with a combined method of physics and data-driven approaches. Here are some references, and thank you very much.